Alright, let's begin. So for this video, we are going to be showcasing the terrain. So the first thing to showcase is the fact that you can be off of the terrain and will not crash the code. So as you can see, I am well off of the terrain, and as I run around it, we can see that the code is not crashing. It is handling everything appropriately. So we are looping all the way through, and there were no crashes. For the area underneath it, we take the B-sphere has scuffed AABB and find out what terrain cells are underneath its minimum and maximum. That composes the rectangle area underneath it. If the B-sphere collides with any part of the terrain, we go in a step deeper, so that has a successful test, and then we do the intended collision volume. Once we get all the way to the point where we have a successful test on the terrain, you can see we have our little screen log being printed out, and we have the successful test right here. So just to hop into the frigate here, we see we have our collide terrain. This is called via the dispatch, which I will cover when I talk about collisions, but that's what it is called when the terrain successfully collides. So for the scene, there's always only one active terrain at any given time. This terrain is drawn during the draw step by the terrain manager. You can set and get the active terrain within this given scene. They are scene level actions. This scene level stuff is with a bunch of setters and getters, specifically for the active terrain. So that means because all scenes need to have an active terrain, we have a null terrain associated with them. This null terrain just has a bunch of empty values if the user has any getters they want from the terrain, but they did not define a terrain yet. It'll either return something with a bunch of zeros associated with it, an up vector, the parameter passed into them, or just a 0. For defining a terrain, I have a brief documentation thing here which lists what each of the values mean, as well as how they define the file path, what each of the floats mean, and what each of the texture step means. So to go in more in depth here, we load in using the map key, the height map, the length, because it's terrains are perfect squares. This is both length and width, the maximum altitude of the terrain, any y offset, the map key for the texture, and then any repeats on the U and V for that texture. So we test to make sure that the height map exists. If the height map exists, we can create our new terrain. And then also if that terrain map ID is not used yet. So for creation of a terrain, we will get the image data using the GL byte. We will loop through doing our nested for loop to update the x and z values appropriately, and then we'll update the y value using an unsigned car, as well as the image data at a given texel index. We use 3 channels instead of 4 because OpenGL does not use the alpha channel, and then that will determine our y value. So we loop through all of that. We then compute the triangle winding. We compute the normals using what we talked about in the rendering class with this weird shape over here to determine each individual normal. This determines all normals that are not on the boundaries of the terrain. So for the boundaries of the terrain, I just went through all of them after computing the inner normals and gave all the boundary points an up vector. So all terrain values have a vector for their normal now. Once we do that, we then can compute the terrain model and then create the graphics object, delete the vertice and triangle lists, get the triangle list from that new graphic object, and then we can create terrain cells. So terrain cells are my way of storing the necessary data for each cell of the terrain. So the necessary data includes the minimum min and maximum max for the cells AABBs, the upper triangle and lower triangle, as well as proper winding for them, and then the normals associated with those triangles. And then lastly, an anchor point, which is then used for the nearest point and nearest normal calculations, which I'll talk about more later. And it also has a bunch of getters associated with it, which is used for the getting a cell and also the testing. This is Skybox. I don't want that right now. So hopping back over to terrain. It's going all the way down. For computing that cell stuff, we will loop through and compute a cell for all the segments of the terrain. Once we do all that, we will add in an extra cell row that just has a bunch of 0 values in it. This is so that when we have our iterator, the ending iterator will never fall off of the terrain and cause an index out of bounds crash. So that's just a precaution there, which I'll cover once we talk about the iterator. We have some getters, rendering. For getting the nearest point, this uses barycentrics, so we find the terrain cell underneath that point. Once we find that, we can subtract the position from that cell's anchor point of the triangle. do some math to figure out if we're on the upper or lower triangle, as well as computing beta and gamma. If we're on the upper triangle, we compute the vectors for those 3 points. Excuse me. Then we compute the height with that. If we're on the lower triangle, we do the same process, except it's now the vectors for the lower triangle, and then compute the beta and gamma. After that, we can set the terrain position using the x and z values passed in by the initial position, and then changing its y value to be that barycentric answer. For getting the altitude, we get the nearest point, so we used what we just showcased. We take that y value, subtract it from the positions.y value, and that gives us how above or below the terrain at a given point is. Lastly, for the nearest normal, we end up doing the same exact process that we did for barycentric for nearest point. The only difference here is that instead of doing the computations for the height, where we just take the y values for those vectors, we instead compute the vector normals instead and multiply beta and gamma with those instead. So for the upper, we do that for the upper beta and gammas, upper normal vectors. For the lower triangle, we use the lower normal vectors. That's it for that. For collisions with the terrain involve defining the space of a rectangle. So this rectangle space is with the active terrain as well as any minimum and maximums. These minimum and max values are the scuffed b-spheres min and max. So for every object within a collidable group, we will loop through all of these b-sphere min and max values, define the rectangular space for it right here, and then we will use an iterator to loop through all the cells associated within that rectangle. So just to bounce back over to here, this involves getting the cell at a given index. We get the maximum and minimum for it. We move the rows around to make sure that the starting row is the upper left point and the ending column is the lower right one. The first cell within any given terrain rectangle is the start row and start column. The last cell is the same start column, but we increment the row by 1. This makes sure that all cells in the intended last row are accounted for, because then it will have to roll over to the next row that is off the rectangle, and that's where we pass the test. This is also why I have that extra row of empty cells, because if the terrain was, say, 32 rows, and the user was at row 32, this would then want to find row 33, which would cause a crash. So we have that extra empty ghost row specifically for this last cell. For the iterator associated with it, this is what we are iterating through to determine each of the cells within the rectangle. So whenever we call the plus plus operator, we increment the column of the iterator. If we ever reach the end column, we loop back to the starting column. If we ever we loop back to the starting column and then increment the row instead, and then we find the cell at that given index. If we are ever in a position for the not equal test where we find that the row is equal to the row and the column is equal to the column, then we can break out. So now that we defined how the terrain cell works, or the rectangle works, we can now explain the actual test. So we loop through each individual terrain cell using the iterator, compute its AABB, do the B-sphere of the collision objects collidable with that cell AABB. Once we pass that test, we can do the collidable's intended collision volume test with the cell AABB. Both those tests pass, then we go through the collision dispatch to call the send collision terrain. And that's it.